Hello guys. Well, this is your first unit in this class, and this is your first of many videos that I'll ask you to watch for homework as part of the flipped classroom. I highly recommend that you take notes on this. Of course, with the video, you're welcome to stop and start it as many times as you need to, so there's no risk of falling behind like you would be taking notes in class. There's other way of taking notes besides pencil and paper, and I'll discuss those in class. But let's go ahead and get started with this unit so you'll see how it goes. The title of our first unit, of course, is the Sun's place in the solar system. We'll look at some learning targets. We have one big learning target that we're going to call a long-term target, and you can read that here. We also have several supporting learning targets. And we'll give you a chance to read those. Pause it and read them. There's some on the next page as well. Okay, so there's our 5 learning targets for this unit. So let's get into this. The Sun is a rather small star compared to all the stars in the universe. We'll learn a little bit more about how our Sun compares with other stars in another unit. But the Sun basically has 3 basic parts. It's got lots more parts than this, but the 3 parts that we're going to look at now are the core, the radiation zone. Actually, it's called the radiative zone. You'll see that in a moment. And then the convection zone. And you can see how hot the core is and how hot the other two zones are. It's kind of hard to see, but the radiative zone is 7 million Kelvin, and the convection zone is 2 million Kelvin. Then the surface is about 6,000 Kelvin, which is considerably cooler, however, still pretty darn hot. Looking at the core, this is where the nuclear fusion, which is kind of the focus of this unit, it's where this occurs. Fusion occurs in the core of stars, or like our Sun. It's the innermost layer, and it's incredibly hot and very, very dense. It's extremely dense in this area of the Sun. Moving outward, you have the radiation zone. It's located just above the core and below the convection zone. And basically what happens here is the light that's created in the core with nuclear fusion is transmitted through this zone on its way to the convection zone. The convection zone is where all that light actually moves through convection cells and gets converted to heat. And then the heat and the light, which escapes the Sun, is then on its way to Earth. So before we can really kind of figure out what fusion is, you have to learn, or at least review, what the parts of an atom are. So here's your definition of an atom. It's the smallest part of matter. It's in all matters has atoms. Whether it's living or non-living, all matter is composed of atoms. And all atoms have at least 1 proton and 1 electron, and all atoms except for 1 have neutrons. So we can kind of roughly say all atoms have protons, neutrons, and electrons, but there is one exception, which you'll see soon. So if you look at a basic diagram of the atom, it's composed of the 3 particles, the protons, electrons, and neutrons. And in the center of atoms, the protons and the neutrons are bound together by a very powerful force. And that makes up the nucleus of atoms. And the nucleus is like the center of the atom. Even though all these particles are very, 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 very small, these subparticles, the protons and neutrons are about the same size, same mass, and they're considerably heavier than the electrons. Electrons are found outside the nucleus, in the space around the nucleus, actually quite a far way away from the nucleus, more than this model depicts. And they're found in different energy levels. There are many energy levels. We're going to explore the first 3 in this class. And they orbit the nucleus, not in concentric circles like you see in this diagram, but they orbit the nucleus in different orbitals, and they move very, very fast around the nucleus, almost the speed of light. So what are these particles? Well, protons are positively charged particles. Neutrons, according to their name, have no charge. Electrons are negatively charged. And since this is we're talking about fusion, we're only going to look at the protons and neutrons, so the electrons at this point will be ignored. So what is fusion? Well, if you just look up fusion in a dictionary, it's the combining of two or more things. In this case, it's the combining of two or more hydrogen nuclei. Remember that nuclei is plural for nucleus. So take the nucleus of two hydrogen atoms and put them together, and that forms a helium nucleus. You'll see that in a moment. So here, again, if you slam two hydrogen nuclei together, that's going to create a helium nuclei, which is the next element on the periodic table above hydrogen. A neutron is going to be also released along with that helium nucleus, but the biggest thing is it's going to produce lots and lots of energy in the form of heat and light and other radiation. Now, fusion is a nuclear process, but it's not the process that we use in atomic weapons, nuclear weapons, atomic bombs, and nuclear power plants. That's a totally different process that we'll cover later in the year called fission. So how does the energy produced during nuclear fusion get across open space between the sun and the earth, which happens to be 93 million miles away? There's no matter out there. There's no particles of matter between the sun and the atmosphere of the earth. So there's only one method that does not require matter to help transfer the energy, and that's radiation. So basically light and heat and other kinds of radiation from the sun travel in rays, just basically straight lines on their way to Earth. The sun radiates energy in every single direction, 360 degrees, and the Earth just intercepts a very small part of that. So finally, our last learning target is going to ask you, what's the expected lifespan of the sun? So I'm going to tease you just a little bit by telling you that the sun consumes, during fusion, about 600 million tons of hydrogen per second. 600 million times 2,000 pounds of hydrogen per second. So NASA and other scientists believe that the sun's going to last about 5 more billion years. We're going to try to calculate that in class to see if they're right. So that's the end of this video. It wasn't too long. At this point, you probably need to go back and take notes. And if you want to write these notes down verbatim, I've tried to make it very, very small amount of writing. This shouldn't be a big issue for you. If you want to paraphrase, but be careful when you paraphrase that you don't leave out something that's critical. Okay, that's it.